Hello everyone, I'm Sandhya Vennapusa studying KCE in NIT Andhra Pradesh. Now I'm going to talk about BFGS method. What is BFGS? BFGS stands for Broyd-Fletcher Goldfarb-Shannon. This algorithm is a quasi-Newton method used to solve optimization problems. It belongs to the family of gradient-based optimization algorithms, and it is particularly useful for large-scale optimization problems where it can be computationally expensive to calculate the Hessian matrix. It is an iterative optimization algorithm that uses an approximation of the Hessian matrix to find the minimum of a function. The algorithm starts with an initial estimate of the Hessian matrix and then updates this estimate at each iteration based on the change in the gradient of the function. The Hessian approximation is updated using information about the change in the gradient and the change in the variables. The optimization problem is to minimize f of x, and there are no constraints on the values that x can take, and we have an initial estimate of the optimum value x0, which iteratively gets better at each stage, and that xk plus 1 is equals to xk plus alpha k pk. It is the next point where pk is such a direction at stage k, and it is given by the solution of the unlog of the Newton equation bk pk is equals to minus gk, where gk is the gradient of the objective function and bk is the approximation of the Hessian matrix, which is updated iteratively at each stage. A line search in the direction pk is then used to find the next point xk plus 1 by minimizing the f of xk plus 1, that is f of xk plus alpha k pk over the scalar alpha k, where alpha k is the step size which can be found by using backtracking line search method. Then we have to find what is the value of bk. So to determine the bk, we have these following constraints: that b should be symmetry and positive definite, and these properties should be preserved in each update, and then bk plus 1 is to be sufficiently close to bk at each update k plus 1, and also it should satisfy the secant equation. Secant equation is bk plus 1 sk is equals to yk, where yk is equals to zk plus 1 minus gk, change in the gradients, and sk is change in the points, xk plus 1 minus xk. Then we formulate this problem as minimum of bk plus 1 minus bk. At bk plus 1, subject to bk plus 1 transpose is equals to bk plus 1. This is to preserve symmetry and positive definiteness of bk. And then secant equation bk plus 1 into sk is equals to yk. And this problem is equivalent to updating our approximate Hessian at each iteration by adding two symmetric rank 1 matrices Z1 and Z2. That is, bk plus 1 minus bk is equals to C1 Z1 Z1 transpose plus C2 Z2 Z2 transpose. If we multiply this equation with sk on both sides, we get this equation where bk plus 1 into sk is equals to yk, that is secant equation. The following choices can be made to satisfy this equation C1, C2, Z1, Z2. If we substitute these C1, C2, Z1, Z2 in this equation, we get bk plus 1, where bk plus 1 is the updated approximation of the Hessian matrix using only previous gradient information. See, we formulate the bk plus 1 using only gradients. That is, yk is equals to zk plus 1 minus zk, and sk is xk plus 1 minus xk. Now we want to compute the inverse Hessian matrix update. In this way, we don't need to compute the inverse Hessian approximation from the starting at each iteration. So we are going to use the Sherman-Morrison-Woodbury formula to inverse the bk plus 1. This is the Sherman-Morrison-Woodbury formula. If we write this equation in the suitable form to apply the Woodbury's formula, we get like this, where A is equals to bk and U is equals to this CV. If we substitute A, U, C, V in the Woodbury's formula, we get bk plus 1 inverse. At each iteration, we update the value of bk inverse using only the values of sk and yk. Yk and sk are given like this, and gk is the gradient of the objective function. This is the algorithm. First, we start at initial guess of x0 and positive definite matrix b0. Then define the maximum tolerance of convergence, that is denoted by epsilon. Then set k equals to 0. Then compute gk search direction by solving the equation pk is equals to minus bk inverse zk. If we want to find the minimum of the objective function, then pk is equals to minus bk inverse gk. Otherwise, if we want to find the maximum of the function, then pk is equals to bk inverse gk. Then choose the step size alpha k by backtracking line search method. Then update the current point. Then find gk plus 1 at xk plus 1. Then compute yk sk. Then update the approximation of the inverse Hessian matrix bk plus 1 inverse by BFGS update formula. This one. Then stop if delta fk is less than the tolerance value. Then set k is equals to k plus 1 and repeat the 4 to 12 steps. This is the code to implement in MATLAB. We give an input f function and x0 initial estimate of x and epsilon tolerance of convergence and maximum the maximum number of iterations. We write the function's gradient and backtracking line search. We have find the optimum values for this function. F is equals to x1 square plus 2x2 square plus e power x1 plus x2, and we give an initial guess x0 is equals to 1 comma 1 and epsilon is equals to 1 e minus 6 and maximum number of iterations is equals to 100, and then we call the function BFGS. For this function we got these optimum values through the shown BFGS MATLAB code. These are the optimum values we got for this function. x1 is equals to minus 0.3128, x2 is equals to minus 0.1564, and the function value is 0.7723. In 4 iterations, we get the optimum value. What are the advantages of BFGS? Convergence. BFGS is a quasi-Newton method. It is known for its fast convergence rate. It can find the optimum solution efficiently, especially for problems with moderate number of variables. And it is memory efficient. BFGS updates an approximation of the inverse Hessian matrix rather than explicitly computing the Hessian matrix, which makes it more memory efficient compared to the methods that require the computation of the Hessian. And it is suitable for large scale problems. And it don't require the second order derivatives, which makes it easier to implement for functions where computing second order derivatives is challenging or computationally expensive. Then what are the disadvantages? Not guaranteed to converge. Although BFGS is known for its good convergence properties, there is no guarantee that it will always converge to the global minimum, especially for non-convex problems, and sensitivity to initial condition. BFGS is sensitive to initial conditions and can converge to different solutions depending on the starting point, which may require careful initialization to obtain an optimal result. The BFGS algorithm is a powerful and versatile optimization algorithm that can be used for a wide range of optimization problems. However, it is important to be aware of its limitations and to carefully select the initial Hessian approximation, the initial parameters to ensure the best possible conversions. These are the references I used. Thank you.